So here we're given a super simple example where we just have a 50 millihenry inductor, and we have some voltage that is applied across it and then some current flowing through it. And here we have a definition for the voltage at some time t, and then we have a boundary condition that at 0 seconds we know that it's 0.75 amps. And so they want us to first determine an expression for the current, and then determine how much energy is stored at 2 milliseconds. So let's see how we might go about this. So for the first part, we recall that IL of t is going to be equal to IL at 0 plus 1 over L of the inductance integrated from 0 to t times the voltage. So it's VL at t in this case, or tau. We usually do a dummy variable, tau, d tau. And so in this case, we get 0.75 plus 1 over 0.05 times the integral of 10 e to the minus 3 tau d tau. That's integrated over t. So we want to look at this part here first. So when we do, 1 over 0.05 is 20, then times 10 is 200, and then integrating factor will be 3, so it'll be minus this, and then we integrate, it'll be e to the minus 3t. So this is our expression, general expression for our current. So if we multiply this out, that's going to be minus 66.67 times e to the minus 3t. Well, we know then also that I at L 0 is going to be equal to some constant, let's say A1, minus 66.67 e to the 0. E to the 0, though, is 1. We know this is equal to 0.75 because they told us that up here. So that being the case, A1 then has to equal 67.42. So now we have our general expression for the current across the inductor with respect to time. It's going to be 67.42 minus 66.67 e to the minus 3t. So this satisfies our boundary condition. When we put t equals 0, we get what our value is there. And so this is our general expression for our current. So the next thing they ask us then is at t equals to 2 milliseconds, determine the stored energy. So at t equals 2 milliseconds, we can solve for that. So IL at 0.002, that's going to equal to 67.42 minus 0.67 e to the minus 3 times 0.002. And when you calculate that out, it should be 1.15 amps. And so we recall then that the energy stored in an inductor at some time t is equal to 1/2 times the inductance times IL at T squared. So in this case then, WL at 0.002 is going to be equal to 1/2 L. We already calculated what IL at 002 was right above here. Excuse me. And we also know the L. So the L is 0.05. That's times 1.15. And so when we calculate that out, we should get 0.33 joules. So again, this is our general expression for the current. This is our energy stored in the inductor at 2 milliseconds.